Hello and welcome to the 5-6 notes. This is a video over substitution. Now, substitution is an integration technique. So I'm going to write that. This is an integration technique. And we often refer to this as the opposite of the chain rule. So it's really the chain rule for integration. So I'm going to make this the chain rule for integration. Okay. So before we do anything, I want to go back and think about what we did on the chain rule when we first learned the chain rule. And the chain rule states this, that if I take the derivative, d dx, of a composite function, so say a composite function like f of g of x, then that's going to give me f prime of g of x times g prime of x. Okay, and so if we want to put an example to this to have this make sense. I think it's kind of hard for us to see what's going on here, but let's do something here. Let's have, let's let f of x equal, say, sine of x, and let's have g of x equal x cubed. Okay, so if I were to write f of g of x, then that would just be me taking g of x, which is x cubed, and substituting it in for x on sine, which is going to give me sine of x cubed, okay? And so if I were to take the derivative of this, then I would get the following. I would take the derivative of my outside function, which gives me cosine, and keep my inside function, and then I would multiply by the derivative of my inside function, which is 3x squared. So, if we think about it, okay, this portion right here, this cosine, this is your f prime, okay? The inside function here is g of x, and then the derivative of your inside function is g prime of x. So I hope that once I go through this, we can kind of see the function notation involved with the chain rule. That's what we've been doing since first semester, okay? So now, my objective here is to go backwards, okay? Is to take the antiderivative of this function. So this is the substitution method. This is the base of it. So if I do this, let's say I want to integrate cosine of x cubed times 3x squared dx, okay? And before when we just had general antiderivatives, we didn't have a rule for this, okay? And what I want to do is to show you the method on how we do this. So, but we call this substitution because we do something called a U substitution. So I'm going to write that out here, that this is really called a U substitution. Okay. Now what I want you guys to notice about this integrand here is that I have a function and the derivative of that function in my integrand. And that's something that I'm looking for when I'm taking an antiderivative. If I have a rule for it, I'm just going to go ahead and take the antiderivative. But if I look at something and it's got a lot of parts to it, then I'm specifically looking for a function and its derivative, okay? And that's going to help me pick my u. So the first thing I'm going to do is do a u substitution here and call this u, okay? So I'm going to let u equal x cubed, okay? Now I'm going to rewrite my integral as the integral of cosine of u and then times 3x squared dx. Now, what I notice here is that I need to somehow get rid of this 3x squared dx, okay, and put it in terms of u. That's the idea. And what I notice is that 3x squared is the derivative of my u. U is equal to x cubed. So let me take the derivative of this, okay? And usually I would say something like this, where u prime is equal to 3x squared, okay? But I don't want to write just u prime. That's not going to help me in this situation. We have to use the ddx notation. So I'm going to say that the derivative of u with respect to x, and I would say that as du dx is equal to 3x squared, okay? Saying u prime and du dx is the exact same thing, okay? Now, my goal right now is to substitute something in for 3x squared dx, okay? Now, we have this dx down here. I have du divided by dx. And I can move this dx out of my denominator and move it to the other side. Technically speaking, we're not allowed to do this, but this is how I explain it. If I multiply both sides by dx, then these dx's go away, and you're just left with du is equal to 3x squared dx, okay? And what I can now do is do another substitution and say that, this 3x squared dx right here can be replaced with a du. And so if I go back to my integral and I write it as cosine of u, and then instead of writing 3x squared dx, I'm going to write what 3x squared dx is equal to, which is just du. Okay. Now, what I want you guys to see here is that I now can take the antiderivative of this. This is something that we know. Okay. And if I were to take the antiderivative of this, that's going to just give me sine of u plus c. Okay. And so now I've taken the antiderivative. It is in terms of u. Now remember that u is equal to x cubed, so I'm going to rewrite this as sine of x cubed plus c. Now hopefully that was the original equation, original function that we started with, and that's what we had over here, okay? So this is the general idea of what we need to do when we do substitution. The other, if you look through this, the process that I just went through is right here, okay? This is the definition of the substitution rule. But the one thing that I want to do is talk about choices for you. That's probably one of the harder things that we talk about with this section. The first choice that we would have would be the base of a function, base with the largest fixed power. Okay. The second option would be an angle measure in a trig function. Okay. The third option would be the radicand. Okay, and that's what's under the radical sign. Okay. The fourth option is the entire radical. The fifth option is an unknown exponent. So an unknown exponent, and that's on a fixed base. And then the sixth one is the entire denominator. Okay. And so that's the gist of it. That's probably the most basic example I can give you guys. I mean, there's probably other basic ones. But I'm going to go ahead and stop this video, and then we will explore example 2 and example 3. So thank you for watching, and we'll see you soon.